Are there any questions? Go ahead, Andrei Gromov.
Okay, I have a question for Leo.
Okay.
It's mostly for my education, I guess, questions. It's not directly related to a talk. So people have studied this 2D thermal melting for quite a while, right? It goes back to
So this is in the smectic
Nelson, KT. Just crystal melting.
Just the crystal. Okay, sure, yeah.
Yeah, crystal, so can go to smectic, can go to pneumatic, all the way down to liquid. But finer temperature. So when you look at these old papers, they never mention the glide constraint. Now, I understand that at finer temperature, glide constraint doesn't strictly hold because there's always some finer density of interstitials and vacancies.
Right.
But do you know why it's like, is it completely unimportant? Because although it doesn't hold exactly, the glide motion is still very suppressed. You know, exponentially probably.
I don't have a good reference at my fingertips, but it's definitely discussed in any dynamics, you know, in a number of dynamics papers, some of the classic ones by Halpern and Nelson, and so that dynamical versions of those, people definitely they definitely discuss, maybe not in the same language as we do now, but they definitely talk about anisotropic diffusion, and the diffusion coefficients for the climb are suppressed by it's not a constraint, it's just a strong suppression that's suppressed at low temperatures by the density of the vacancies interstitial. So it's definitely there in the literature.
Does it change the transition? Oh, go ahead.
Well, so
I was asking if it affects transition.
Well, in 2D, there's really no transition, strictly speaking, in finite temperature, because if you're in 2D, 2D smectic is actually unstable. So this is actually, once you unbind dislocations, this guy just undergoes a long crossover, and it's a very interesting crossover. And this is what's studied by Halpern, and second author's name is escaping me, but they did this anisotropic melting in the thermal case, and there's a long crossover from a crystal. Once you unbind dislocations, you go to a pneumatic at asymptotically long scales. There's really, smectic is unstable in 2D at finite temperature.
And in 3D?
Well, so then in 3D, this transition is not understood. Or I should say, there are two theories, competing theories for it. They're actually in agreement with each other. One is Toner's theory of dislocation unbinding at finite temperature. And the other is Tom Lubensky's theory, is more like a Ginsburg-Landau-Dejean theory. The problem is neither theory, while they're consistent with each other, theoretically it looks like a great picture, but neither of them, both of them have problems with experiments. There have been some extremely exquisite experiments by Bergeron and Carl Garland, Bergeron scattering, like X-ray scattering and light scattering, and Carl Garland thermodynamics, like heat capacity. And there's disagreement, pretty basic, at a very basic level, between the theoretical predictions and experiments. And so that question of smectic to pneumatic transition is, I would say, is one of the enigmas of classical statistical, critical phenomena.
Is glide constraint part of the conversation there?
It's not, because, you're doing statistical mechanics, they're not doing dynamics. Once you're doing equilibrium statistical mechanics, dynamics is kind of irrelevant, as long as it's not a strict constraint, as long as it's just, if the system can get there, the assumption of statistical mechanics is you wait long enough for it to equilibrate. So it's not a,
I
studying dynamics.
It's like order of limits, right?
Huh?
Order of limits, basically order of limits solution, right? You
well,
first say that.
Not really. I mean, you're doing everything at, if you're really trying to say classical liquid crystals, they're mostly at room temperature. So that constraint is not a very strong constraint. It's just a suppression. It's very anisotropic. So you would need it in dynamics. If you were doing dynamics of that transition, Hohenberg and Halpern kind of thing, then it would matter. It would not matter for critical properties, but it would matter for, for details, I would say.
Good, thank you.
Yeah.
Easy.
Yeah, I have a simple question for Leo. For the time reversal symmetry breaking semantic phase, you have a term like UX partial T UY. That term is the coefficient related with something like odd viscosity or Hall viscosity in quantum Hall state?
You mean here?
Yes, the core, yeah.
No, that's just a pure, no, it's just proportional to magnetic, background magnetic field. It's just the standard, it's the same term that you have in the ordinary Wigner crystal. It's
Mhm.
the,
I see.
it's the, if you go to the limit of zero mass,
Mhm.
this is the term that controls the dynamics. It's the
Mhm.
cyclotron motion, basically.
I see.
Well, it's the guiding center motion dynamics.
I see. So in principle, there are other time reversal symmetry breaking term, but they are less relevant, so it is ignored here. So in principle, we
Yeah,
can have a partial x ux, partial t, partial x uy term, something like that.
Right. I would say these are the, this term just comes from, this is nothing more than, a dot v drdt.
I see.
Yeah, and an a for constant b, this just becomes r cross, r dot.
I see.
So that's really all that is. And
Yeah.
the cute thing about it is in the crystal phase, ux and ui are both Goldstone modes. When you go to the smectic state, it's only the ui that's a Goldstone mode. However, ux is still necessary because it's canonically conjugate to ui. And so you still need to keep it around. It doesn't have any meaning in terms of, because now you have dislocations, so it doesn't have any meaning in terms of single valued phonon, but it's just a canonically conjugate momentum to ui.
I see. And for fractional quantum Hall state, the coefficient is the same. It doesn't depend on which kind of filling or which type of Laughlin state are you there. I mean, it's always 1 over L squared.
It's 1 over the magnetic length squared. So it's, it's set by the magnetic field, but, I haven't really thought about incompressible states, so all this is sort of, a little bit of hand waving at this stage for bosons. In other words, quite a bit of hand waving and just sort of sketching things out that I'm interested in, as far as sort of trying to get to the fermionic version of these. At the level of atoms, bosonic atoms, I understand it, but so compressible states, but for incompressible states, I don't really have a theory of it.
Right, thanks.
But my point here is that this is one way to get at a theory of the nematic, quantum Hall nematic, for example, or quantum Hall smectic, which incorporates not just the phonon degrees of freedom, elasticity, but also quasi-particles, if you're careful about keeping track of dynamics of the defects that you unbound, simply because you have a complete theory starting with a crystal.
Thanks.
Thanks.
Are there any other questions? I see, Andre, you still have your hand raised, but I don't know if you just never lowered it.
I never lowered it, sorry.
Okay. I have a question for Yichen. At the end of your talk, you mentioned some numerical methods to make progress.
Yes.
Could you say something about what you meant?
Well, that's the hope that we can do something by building a lattice model and then using, say, DMRG or something like that to study. But we haven't really think too hard on that perspective. But I think so we try to think about this along the line of couple wire model, and we have some result, but it's not very decisive. So that's why I mentioned this as an outlook, so that we can literally really translate whatever we have into a lattice model and then do numerics on it.
I see. Okay. I was wondering if you had something more abstract with like the algebra, if that makes sense.
Yeah, Jeffrey, do you have any comments on that?
Yeah, no, not that I know of. I don't know of any lattice model that give similar gauging mechanisms.
Awesome, thanks. I also have a question for you, Leo. You mentioned quantum crystals, and I guess this is a very basic question. Does that mean that like there's something like very different when you go at lower temperatures? So is there like what's the difference between quantum crystal and classical crystal in this sense?
Well, it's
Or is there like an important difference I should have in mind?
well, I mean, it's the same. It's the same phase, but it's zero. What I mean is a zero temperature phase where the momentum, it's the usual thing that the momentum and position of phonons and the corresponding conjugate momentum don't commute. So in a bosonic case, there's nothing beyond just harmonic oscillators, coupled harmonic oscillators. But if you now generalize this to maybe fermions or maybe more exotic particles, then there could be additional phases that come into your path integral. But all I mean is that you have the dynamics is the same, but then you're at the level of path, you have to do a path integral rather than minimize the action, if you wish. So that's my approach to all of these problems, and I've been able to get away with it because I focus on bosons for now, where you try to understand the right dynamics, the right kinematics for the at the classical level, the right energetics and then kinematics, and then you quantize as the usual way, either operator or path integral, and so that's all I mean by that.
I see. So aside from being close to a phase transition, there's no like crossover as you lower temperature or anything like that.
Yeah, I mean, I've been thinking about zero temperature phase transitions for the most part. So, there's a kind of a fundamental question. If I have I have a state like this and I have a state like this, how do I go between them? What is the field theory that describes that transition in 2+1 dimension, let's say, or 3+1 dimension? So my claim is theories that I wrote down is a complete description of this phase transition. And it's a coupled gauge theory, and that gauge theory has 3 sets of gauge fields, and they're coupled in this very non-trivial way. But fundamentally, it's a Higgs transition. But so at the mean field level, all I do is I simply say that, the simplest level, I simply say that, well, I Higgs out once some matter, the dipole matter condenses to take me from one phase to the other, then this gauge field gets gapped out. But that's not the actual criticality of this phase transition of this model has not been studied. Like what are the critical properties of this model as you tune to this critical point beyond this sort of this is just a way to get the phase, this condition. But what is the actual critical properties from any layered state, a smectic state to a nematic state, or its counterpart from a crystal to a smectic? What's the critical property of this model? It hasn't been explored. If you wish, it's the quantum analog of the Lubensky-Ma theory, a billion Higgs model, except this is a more complicated version of it. It's matter coupled to gauge fields, but there are 3 sets of gauge fields if you're doing this transition. And with quite a non-trivial Maxwell term, which has this extra, which has this very non-trivial coupling between the gauge fields. So I don't know the critical property of this transition. That's an open question.
I see, thanks. Are there any other questions? So do one of the organizers want to step in now?
Yeah, okay. So if there are no more questions, thanks everyone for joining us today, and that will bring us to the end of the talks for today. But we also have this Discord channel set up, which you would have gotten a link to if you are registered. And so if you're interested in discussing more about any of the talks or just chatting with anyone, then you can join us there. So okay, we'll see you there. Okay, thanks.